Hello, everyone, and welcome to today's webinar in the CERDUP and ESTCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDUP and ESTCP. The webinar will consist of a brief overview of the two programs, followed by the technical portion, which features research on battery storage implementation to increase resiliency at Department of Defense installations. Dr. Jeff Marquesi of the National Renewable Energy Laboratory and Mr. Craig Schultz of ICF will present storage resiliency results from simulations that several leading microgrid organizations performed under contract to ESTCP. Jeff and Craig's joint presentation will be followed by a question and answer session. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use with Zoom. If you lose the content on your screen, or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please feel free to call onto the conference line shown here. You may submit a comment using the chat box if you have continued technical difficulties. The Q&A option should be reserved for questions for the speakers. Because today's broadcast will be listen only, you can submit your questions using that Q&A box on your screen. Please don't wait until the Q&A period to submit your questions. We do encourage you to submit them throughout the presentation. When submitting your questions, please make sure to add your organization name so that we can identify you during the Q&A. With that, I would like to introduce Mr. Timothy Petro, who is the ESTCP Program Manager for Energy and Water. Before joining CERDUP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim?
Thank you, Rula, and welcome everybody to today's CERDUP and ESTCP webinar. I'm going to provide a few slides to give an overview of the programs and then hand it back to get the presentation started. CERDUP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, Department of Energy, and the EPA. CERDUP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERDUP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERDUP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERDUP and ESTCP are complementary programs with much of CERDUP research occurring in the lab and pilot scale, while occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally support lab efforts are conducted. There are 4 program areas in CERDUP and 5 in ESTCP. The Installation Energy and Water program is only on ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, are both CERDUP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focused on research and demonstrations conducted under the Installation Energy and Water program area, Installation energy and water has essentially three main areas of research: smart and secure installation energy management, efficient integrated buildings and components, and distributed generation. Our webinar series highlights research and demonstration efforts from each of the five program areas. As you can see, upcoming webinars will cover a broad range of topics, including development of environmentally friendly pyrotechnic and propellant formulations, compound-specific isotope analyses to document contaminant degradation in groundwater, ecosystem restoration and optimizing recovery of plant communities, and risk assessment at PFAS-impacted sites. You can find additional information about upcoming webinars at this link. I would also like to remind you that a copy of this presentation of today's session can be downloaded from our webinar webpage. Also, we'd appreciate if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. With that, I hope you enjoy the webinar today, and I will hand it back to Rula.
Thank you, Tim. It is now my absolute pleasure to introduce our speakers for today. We have two speakers. Dr. Jeff Marquesi is going to start us off. Jeff is a senior research advisor at the National Renewable Energy Lab. Prior to joining the lab, he served as a chief scientist at Noblest, a nonprofit science, technology, and strategy organization. Jeff has over 20 years of government leadership in research, technology development, and policy aimed at making the DoD a more sustainable and effective organization. At DoD, Jeff served as the executive director of CERDP and ESTCP, and before joining DoD, he worked at the Institute for Defense Analysis, at Stanford University, at the University of California, and at the National Institute of Standards and Technology. He earned a doctoral degree from MIT. Our second speaker is Mr. Craig Schultz, who's a senior advisor at consulting firm ICF in Fairfax, Virginia. Craig focuses on renewable energy and energy security issues for military installations and other large energy users. He leads ICF engagements ranging from market assessments and feasibility analyses to project selection, policy formulation, transaction structuring, negotiation, and implementation. Craig has been working with ESTCP since 2010 on battery storage and microgrid economics and reliability performance. He earned a bachelor's degree with honors from Wesleyan University and an MBA with honors from the University of Chicago Booth School of Business. Jeff, I'll go ahead and turn it to you now.
Great. Thank you, Rula. What we'd like to do today, Craig and I, is to give you some insight into some ongoing ESTCP initiatives that are examining the role of energy storage and its value for energy resilience on military installations. When we talk about energy storage, we're talking about multi-megawatt stationary batteries integrated into a microgrid. So have slide 17, please. The agenda for today's webinar is listed here. I'm going to first review the objectives and the program structure for this initiative. And as you'll see very quickly, a key aspect in understanding the value of storage is understanding the baseline performance of a microgrid without energy storage. I'll then talk about the reliability performance of such a baseline microgrid. At that point, I'll turn it over to Craig, who will talk about the baseline economic performance of the microgrid without storage. Then he will highlight some of the recent results from the last year of analysis done by the ESTCP contractors. We'll conclude the webinar today with a discussion of the future plans that will be executed this year and in future fiscal years. Slide 18. So the objective of all this work is to quantify, demonstrate, and validate the value of energy storage in a microgrid. And quantify is really the key word here. There's an enormous amount of discussion in the energy community and around the Department of Defense about the value and promise of energy storage. But unless you define what services you value and how you quantify their performance, we're only talking in vague qualitative terms, often comparing disparate value streams that may or may not be relevant for the military mission. Decisions on future investments need two key things. We need to understand quantitatively the performance and cost to justify any investment decision. And second, we have to have confidence that a properly engineered system can produce the results claimed for these technologies. And that's what this program has been aimed to do. The key issues are obviously twofold. First, reliability. We create microgrids to ensure we have power and grid outages. What is the likelihood we'll have that power? That's what we mean by reliability. The second is life cycle costs. What is the cost of this resilient energy solution, and in particular, compared to other solutions? Because, as I'm sure all of our listeners know, investment decisions for energy resilience are not made in a vacuum. This work needs to be couched in terms of the improved performance and hopefully lower costs relative to other solutions. And in this work, we've asked people to compare storage-enabled microgrids to a baseline microgrids, which are constructed from traditional emergency diesel generators, photovoltaic systems, which are not available during the islanded time, and standard UPSs for ride-through capability. So the real question is, what is the added value when we integrate storage in this system? We know that this baseline that we're comparing to is not the standard baseline of military installations today. In fact, the most common energy resilient solution is a set of standalone generators tied to individual buildings. But we also know from previous ESTCP work that a microgrid based on diesel generators shows enhanced performance and better life cycle costs than that current solution. So when we're looking to advance microgrid technology by integrating storage and large-scale storage, as I said, we really want to understand it relative to this microgrid baseline. Before entering a little bit about how we're doing this, I want to lay out the motivation for ESTCP in tackling this problem. As many of the folks will know, DoD has had a significant effort for the last several years in procuring and installing large-scale renewable generation on our installation using multiple different economic methods. These PV systems are both in the ground or soon to be in the ground, represent a very large local distributed energy resource. And they have been effective in an economic sense in lowering the annual energy costs for a military installation. But as currently used today, they provide no additional energy resiliency and thus do not directly contribute to the military mission. So the question we'll be examining during this webinar and the future work to be conducted is, how can we exploit this very large new resource of military installations, and what is the value of exploiting it by integrating large stationary storage? Slide 19. So let's think about and examine this comparison. First of all, what are we talking about when we talk about reliability? We're specifically talking about the reliability during a grid outage when the microgrid is islanded from the commercial grid. And we want to understand the likelihood of being able to achieve the power to support critical loads from between 1 and an hour to a week-long outage. The results we'll show you will be for that duration of outage and shorter durations, but are applicable for longer outages as well. And we also want to understand the net life cycle costs. And Craig, later on in this webinar, will go into some detail on how we define that and how we calculate that. But that includes the capital costs, the O&M costs, potentially avoided costs, potential revenues. And we want to boil that down to a simple metric, which is the average annual cost per peak kilowatt of critical load. That way you can compare costs across installations. Now, these two metrics, the technical reliability and net life cycle costs, are not independent of each other, obviously. one can easily design an extremely reliable system, which is way too expensive. One can also similarly design a very inexpensive system, but it doesn't provide the backup power reliability that the military missions require. So what you will see in these is work done by a number of teams to try to analyze the trade-offs between these two key metrics and to come to an optimum solution, which gives, at a minimum, the needed reliability the military must have for its critical loads, and a cost which is competitive and therefore lower than current solutions. As I said before, these will be compared to a baseline microgrid, which will consist of some level of PV, an N+1 backup diesel generator system, which I'll define a little more specifically, and UPSs. Can I have slide 20? ESTCP initiated this program in a phased approach. First, ESTCP wanted to know quantitatively the value new storage potentially could provide. We needed to define the bar that we might test to in the future, and to understand, is there enough value if these technical performances can be achieved in real operations to merit even doing a demonstration. That is what has been conducted in what was called phase 1, which are detailed simulation and modeling exercises under FY19 funding. 6 research teams were selected through a competitive solicitation, which was issued back in January 2018 and funded last fiscal year. Phase 1 has been completed, and during this webinar, we'll review that efforts and highlight the results that have been seen by many of the researchers. Phase 2 has to do with taking some of those results and seeing if they are feasible in an engineering sense. One of the lessons the ESTCP in the energy space has learned through the last several years is that the cost and time of going from an analytic assessment to a field demonstration is extremely hard, and in fact involves too much risk and limits the innovation cycle. So one of the things that Tim has initiated in the ESTC's energy and water area is to, when appropriate, go first to a hardware-in-the-loop testing, which will allow in less than a year to go through multiple cycles of innovation and examine what are the feasibility, what are the problems, what are the solutions in an engineering sense. And then for successful hardware-in-the-loop demonstration, then consider going to a field demonstration. Phase 3, which will be initiated in FY21, is a more traditional ESTCP field demonstration, and we are currently looking for partners to host those things. We'll talk about that, what's required in that partnership in a later point. Slide 21. So let's talk about the phase 1 conditions first. So phase 1 is a techno-economic assessment conducted through modeling and simulation. ESTCP's goal was to understand the value proposition, which again is both the reliability and lifecycle costs for DoD installations in general. But as I'm sure people on this webinar know, the results of such a study are always dependent on the site-specific conditions, on the assets an installation may have, on the conditions of the local electricity market and such. So phase 1 was conducted for 7 different DoD installations using realistic conditions found on those installations. And this chart lays out the type of variables that were considered. The first 2 boxes, starting from the left, really define the problem. The first box, the military installations, lays out what are the critical loads we have to protect, what are the solar assets that are available to exploit through a storage system, and what are the electric rates which set the baseline cost for providing power to an installation. So 7 different configurations were designed for that. The second box, also part of the problem, is where does this installation lie in terms of the energy market? What are the rules? What are the prices? That defines, in some sense, what the opportunities are one can exploit in an economic sense. All the conditions described in these first two boxes were developed and provided by ESTCP to the researchers who were supported. The second two boxes really describe the potential solutions to the problem of energy resiliency exploiting storage. First, the question of what type of hardware or technologies could be brought to bear. This was left up to the individual researchers to propose a variety of different technologies, different lithium-ion batteries, because lithium-ion is a family of batteries, not a single type of technologies. People looked at flow batteries, and there were other things, smart fast switches, ultracapacitors, and etc. The second part of the solution is, how do you configure them? What size do you set the storage at? What's your operational approach, both while islanded and when grid tied? Because those things, both the selection of the technologies and the design of its configuration and operation, determine what the performance will be. And those, you'll see, will vary between the multiple investigators and have given ESTC some insight on what the potential solutions are. Slide 22. I want to now turn to the first issue, which is important in understanding performance, which is a reliability performance baseline. Slide 23. First, let's set the stage on what these reliability is for. As I said before, we are considering 7 different installations that are all being modeled, and the key information on their loads and the distributed energy resources are shown on this slide. These range from very large installations, such as Fort Bliss, which is listed at the bottom of the slide, which has over a 10 megawatt peak load, to very small reserve bases, March and Westover, which are listed on the second and third row, which have on the order of only 1 megawatt of peak critical load. The other installations, Holloman, Corpus Christi, Pax River, and Ventura County, are in the range of typical active military bases across the services. And as you can see, their peak load ranges from 4 to 8 megawatts. We also wanted to understand a variability of PV. And the key characteristic to look at the variability of PV is how much PV you have relative to your critical load. So as you can see here, the PV systems range from roughly 25% of the peak critical load to over 100% of the peak critical load. Depending on your relative PV capacity will determine how much energy you can store in your battery system and how much that will contribute to a resilient energy solution. For each of these installations, we then defined the baseline diesel-only microgrid. For each installation, we selected a size for these generators. They range from 250 kW up to 2 megawatts. That size was selected based on engineering judgment and standard practice used in the industry. Then the microgrid was configured to ensure it had an N+1 reliability. By that I mean we selected the number of generators to be 1 more than would be necessary to meet the peak critical load. And those values range from 4 for the very small reserve bases to up to 12 for Pax River. To make sure we could meet ride-through capability, i.e. the portion of the load which cannot afford any even momentary interruption in its power, we also assigned a number of standard UPSs whose sizes and numbers are listed on this chart. So this defines what the baseline microgrid diesel-only generator system is. And I want to talk now about how we went about calculating the reliability performance and what those metrics actually look like. Slide 24. So for each installation, we've gone through a calculation to define the reliability metric. The metric ESTCP chose was to define the probability that all critical loads will be supported as a function of outage duration. To set it in other words, I have X amount of critical load, which varies hour by hour through the year. What's the probability that I will be able to supply power to manage 100% of that critical load? Now, there are multiple metrics one could have chosen. One could have calculated, and we have calculated, what the potential loss load might be. All these metrics are highly correlated, and so the relative performance you will be shown later on is going to be independent of the specific metric chosen. And so we will just be showing you these metrics, but this is a more general characteristic about relative reliability. So in the baseline diesel generator system, the only reason you have failure, assuming as we have that we have sufficient fuel available on the base, is if a diesel generator fails or is unavailable during the outage. And the outage could take place at any hour during the year. And so you have to assume that the outage may start from January 1st, right after midnight, or at December 31st, and it can run up to a week. There are three reasons that a generator may not be available to support the critical load. First, it could be not available. That is, it may be offline due to required repair from some previous failure or from a maintenance event. It can fail to start, which is quite a common event for poorly maintained generators, and it can fail while running. These reasons need to all be considered when looking at the reliability of a generator-based systems. Supported by ESTCP, NREL did a detailed analysis of existing empirical data that's been collected by both the Army and Navy to define what the performance of well-maintained generators are. And the numbers you've seen here are a result of that analysis. Availability of diesel generators is quite high. The reason they're quite high is that they're not called on that often, so the probability they'll be offline due to a failure is quite minimal. They're also quite available because traditional maintenance takes an hour at most, and therefore when you're considering outages that may run up to a week, they'll be put right back into service immediately. Failure to start has been shown to be a fraction of a percent for well-maintained generators. I will tell you that when you have poorly maintained generators, it is multiple percents and quite different. But we're assuming that generators are maintained properly, which means that they're maintained in accordance with the UFC criteria. The final characteristic is the mean time to failure, which we've estimated to be 1,700 hours. Poorly maintained generators can fail within a day or two on average, but well-maintained generators will last this long. But if you're looking at multiple generators for a week-long outage, you have to expect a certain number of failures. So this is what defines the performance of individual generators, which constitute the system of generators in a microgrid. We set a minimum performance requirement for this baseline generator to be equal to the reliability provided by this microgrid for a constant fixed load equal to the peak critical load in a year. But I want to also show you what happens when you look at a variable load, which is what we face in reality, and for comparison, show you what happens with the traditional non-microgrid solution when you could afford to put 2 diesel generators on every single building. Now, in fact, I think as most people know, that's not the common solution, but it is done for the most high priority critical loads on military bases. So let me first, in slide 25, walk through some of these results. I'm just showing it for the largest and smallest base, Fort Bliss on the right and Westover. So what's plotted here on the y-axis is the probability that this microgrid or backup generator system will be able to supply sufficient energy to support 100% of the critical load. This is plotted as a function of the duration of the outage. Remember, the outage can start at any time during the year, and that is one of the things that contributes to the probability distribution function. So we've plotted from 1 hour up to a week in hours. So let's look first at the right at Fort Bliss. So please note that both these plots only go to 80% and are not from 0% to 100%. The blue line, which is the central line, is what was set as the minimum performance requirement for the investigators to meet. That is the reliability you would expect for an N+1 diesel microgrid supporting a fixed load equal to the peak critical load. Now, one thing to point out about this is people often assume that they can get multiple nines of reliability for diesel-based systems, and that is a myth. It cannot be achieved with current technology. But the upper line in orange, labeled variable load, shows what a N+1 microgrid diesel-only system would provide in terms of reliability. As you can see, this is not multiple nines, but it is at least 2 nines throughout the duration. The reason that you have a much higher reliability under variable load is that most of the time, the load is much lower than the peak critical load. And so your system of network generators, N+1, which was designed to have 1 extra generator at that peak critical hour, during most hours actually has 2 or 3, if not more, additional generators that can be called upon if one fails. I'd like you to compare that to what the probability of meeting 100% of the critical load if you had not a microgrid, but 2 generators tied to each building with a critical load, in this case, assumed to be 100 buildings. That is the yellow line. You see that that very rapidly dies off. What that's telling you is that in the absence of a network solution, the likelihood to meet all your critical load is much lower than most people's expectations. Not shown on this chart is what would happen if you had only a single generator tied to each building, because that would be even worse and would fall off within the first half a day to below, visibility. Similar results are shown for a small base, in this case, Westover Air Reserve Base. In that case, because the number of buildings is relatively small, the difference between an N+1 microgrid and 2 generators per 5 buildings is very similar. And again, remember, that's the minimum performance we are saying must be met for satisfying the military requirements. But if you look at the performance of an actual diesel microgrid under variable load for this base, it's up at 99+% during those hours. So these set the performance requirements that we wanted to compare an advanced storage-enabled microgrid to. Again, we're not setting the baseline as what would be performed by standalone generators. We're setting it by what would be performed by a diesel-only microgrid. Now, let me turn it over to Craig to discuss the economic baseline and highlight the results that have been achieved in phase 1. Slide 26.
Thank you, Jeff. Before beginning, let me also acknowledge ICF's partner firm, MPR Associates, with Paul Duncan as technical lead, that was a key participant in this analysis. Slide 27, please. In this section, I'll be talking about the baseline results on the economic side. Jeff just covered the baseline results on the reliability side. So if we go to slide 28. This slide shows the key economic metric for this R&D program. That is in the far right column. It's the net annual cost of protecting each kilowatt of peak critical load at each military installation. In other words, that is the net 20-year cost of adding the microgrid and all the energy security assets in it before introducing battery storage, which we'll then compare to that baseline later. In other words, taking the first row as an example, it costs $98 annually to protect each kilowatt of critical load with the baseline microgrid at Holloman Air Force Base. With a critical load of 5,996 kilowatts, just about 6 megawatts at Holloman, that comes out to $585,000 per year, just multiplying the critical load times $98. That's also the difference between the middle 2 columns in this chart divided by 20 years. It's the difference between the electricity costs without the microgrid and with all the microgrid elements added. You could compare that to what Holloman currently spends annually to procure, operate, and maintain all the standalone backup diesel generators and UPS it has, if you want to know whether a microgrid without battery storage costs more than the status quo. That, as Jeff noted, that, however, is not the purpose of this specific research program. The purpose on the economic side was to compare this metric, the one on the far right, between a microgrid with and without storage. That is important because we want to isolate what, in a realistic long-term sense, it costs to include battery storage in a microgrid when you still need to meet reliability requirements. And we want to do so annually to include all the cost additions and subtractions in it. That's what we mean by net costs. And to standardize that by what it is serving mission-critical loads. We want to pinpoint where microgrids effectively cost you more or less on a life cycle basis among installations and compared to the status, and compared to microgrids with storage. To that end, you'll see large variations between baseline microgrid costs on this chart at Fort Bliss or Corpus Christi and those at March Air Reserve Base, if you look on the far right. The next slide explains why. Please go to slide 29. You will see that the far right column here is the same as on the last slide. The formula to build it up is simple. Just add the cost in columns A, B, C, and D to get the sum in column E. That is, add the costs of a centralized set of new diesel generators with N+1 redundancy, the same assets Jeff described on the reliability side, new UPS, also with N+1 redundancy, the microgrid to control the generators, UPS and PV, and then column D, any savings you can obtain from these microgrid assets participating in demand response or peak shaving on electric utility bills. Now in this chart, you'll notice differences in the costs and savings between the installations. March Air Reserve Base has a total baseline microgrid cost of $416 per annual kilowatt, while Fort Bliss is 5 times lower at $83. Most of the reason on the cost side is scale. March is only protecting 600 kilowatts of critical load. You'll see that in the second column from the left. While Fort Bliss is protecting 20 times as much critical load. It's important to remember that many of the costs of a microgrid are fixed and do not vary with load. So Fort Bliss enjoys economies of scale on that part of the costs, as well as on some of the generators and UPS. As to the demand response and peak shaving savings, some installations like Corpus Christi have high peak demand charges on their utility bills and participation options for demand response. They can save quite a bit through operating this baseline microgrid for economic purposes. Savings of $34 per kilowatt annually pays for 70% of the microgrid all its own. Other installations like Fort Bliss and the 2 California bases, March and Ventura County, have utility tariff or state policy barriers to running diesel generators for economic purposes, and therefore see zero savings in column D. It was the job of the 6 investigators selected competitively by ESTCP to analyze the contributions of battery storage to microgrids, and for NREL to also do a parallel comparison to see if and how they could beat these baseline economic results when they add a whole new column of cost to the equation above. So when we discuss in a few moments the storage-enabled microgrids, they in essence have all these costs, A, B, and C, but they also have all the costs of adding the storage and integrating it into the system. So it's important to see, in doing so, can they reduce the diesel generator costs or the UPS costs? Can they increase the demand response or peak shaving savings? And can they introduce new savings from shifting time of use energy consumption patterns or from wholesale electricity markets like frequency regulation while meeting or bettering the baseline reliability requirements that Jeff discussed? That's the standard, the baseline standard they had to beat. Let's turn to the next section to see. Please go to slide 30. In this section, we highlight how the battery storage enabled microgrids performed that were modeled by the 6 investigators in NREL on economic and reliability metrics compared to the baseline. Please go to slide 31. Here's a list of the 6 investigators that did the storage modeling. All of them are well-regarded organizations with both pragmatic experience as well as microgrid modeling simulation expertise. The names of their research programs are on the right part of this chart. They spent the better part of 2019 analyzing and reporting the microgrid performance for ESTCP, and the results are near final at this point. While they all approached the same problem statement, and they all had the same baseline metrics they need to clear on the reliability and economic side, they approached in widely different ways, with different battery technologies in different sizes and combinations, operating in different ways with different simulation software. So it's a real competition about how to solve the same problem with many talented teams approaching it. To get a taste of the results, please go to slide 32. The results on this slide and the 5 that follow are preliminary because the contractor reports have not been published yet, but they should be quite representative of the final results, and they will be published by ESTCP soon. There were 2 types of key reliability metrics. One is shown on this slide and the other on the next. The first, which Jeff went into in some detail, is whether the storage-enabled microgrid can cover 100% of a military base's critical load for power outages starting randomly at any hour of the year, and that can last anywhere from 1 hour to 1 week, or 168 hours. As the verbiage on the left side of this slide shows, storage-enabled microgrids from across the 6 investigators tend to meet or better the baseline requirement. That's not surprising given that this was the research objective. The interesting parts are by how much and why, and whether that can be done while simultaneously lowering energy security costs. The chart on the right, it is an example from one contractor for Westover Air Reserve Base, though it's representative of many of the results. BESS in the chart stands for Battery Energy Storage System. The y-axis is the length of the x-axis is the length of the power outage, and the y-axis is the probability that all critical load is covered during that outage. First, the outperformance is substantial. The baseline requirement is the blue line here, and if no diesel generators are removed, the battery-enabled microgrid performs at the red line. So that's the result when the investigator added the battery and did not deduct diesel generators. And you can see it's almost perfect for the entire duration, and well above the baseline and even farther above the likely performance of standalone backup generators. The second interesting observation is that when one of the 4 generators in the Westover microgrid can be removed when you add storage, that's represented by the green and purple lines, they still beat the baseline requirements. So that's important because it speaks to whether overinvestment in diesel generators can be reduced if you add storage. If you can do that while meeting or bettering the reliability requirements, you save $560,000 of capital costs for each of the 750 kilowatt new generators, plus $7,000 every single year in O&M and testing costs for the generator. Now we can see the other main reliability scenario as we turn to slide 33. This slide has the same X and Y axes as the prior slide. What it shows is how well the storage-enabled microgrid meets 130% of the peak critical load, i.e., if there's some unprecedented, unplanned for upsurge in critical load needs at the installation, or there's a reassessment of what is critical load during a long outage, how does the storage-enabled microgrid perform? The red line displays the storage-enabled microgrid's coverage of 100% of the critical loads, which again is well above the baseline and close to 100% for a long duration. It remains above 95% through about 20 hours. When you need to meet 130% of that level, the performance can be seen in the bottom light blue line. It remains above 95% for about 20 hours and declines over time as the odds mount that more than one of the diesel generators and or the battery system will fail to provide power. The other reliability scenario we tested was what happens after the on-installation fuel supply is exhausted during the power outage. If you have no battery to store or meet out power from a PV system, there's virtually zero coverage of critical loads if you don't have diesel fuel. When you have batteries connected to your microgrid, we tested how long 10% or 30% of critical loads could be served. What the investigators found was that in many cases, those loads could be served for 24 or more hours at 95% or higher reliability. But in others, the coverage lasted only a few hours. Where storage-enabled microgrid fell on that metric, how long it could protect loads when there's zero diesel fuels on base, depends largely on the ratio of PV capacity and battery energy, megawatt hours, on the base to its critical load. If a base had quite a bit of PV and battery storage relative to its critical load, not surprisingly, it can provide some coverage of critical loads for many hours even without fuel. For example, at Holloman Air Force Base with 5 megawatts of PV relative to 6 megawatts of peak critical load, if you take 10% of that load, you have an 8-to-1 peak PV to peak load ratio. Adding a multi-megawatt battery in that setting offers quite a bit of resiliency even without any fuel supply. On the other hand, if you don't have high ratios of PV and battery to peak loads, the coverage of even 10% or 30% of loads at any level of reliability only lasts a handful of hours at best. Next, we'll switch from the reliability to the economic results. Please go to slide 34. The most striking observation about the economic results was their variation. As you'll see in a moment, there were widely divergent outcomes among the installations, largely due to reasons outside of the military's control or microgrid vendors' control. The divergences were in both the level of savings and their sources. What activities accounted for most of the savings? There are locational reasons, such as whether an installation is in a market with robust wholesale opportunities for battery storage participation to gain revenues from ancillary services or energy or capacity markets, and if and how the installation's rates with its utility and its competitive generation supplier reward peak shaving and time of use energy shifting. If peak demand charges are low and not differentiated between seasons, and if the installation pays the same energy rates all year long, then the battery can't contribute much to retail bill savings. And the opposite is also true. There are also factors related to the batteries selected that drive the economic results. For example, lithium-ion chemistry batteries tended to outperform other chemistries, especially when paired with fast-responding equipment and controls, such as ultracapacitors and phasor-based controls. Contractor choices of how they configured and operated the batteries mattered as well. Lithium-ion batteries with a high-speed companion tended to be a way to reduce the number of UPS needed. And if you can do that, you can eliminate $160,000 in capital costs per UPS and about $3,000 in annual O&M costs. That's for a 250 kVA, 15-minute UPS. When the battery system could perform the ride-through function itself, you could eliminate UPS and create annuity savings. Battery duration for all chemistries can affect if and how many diesel generators can be safely eliminated from the microgrid to achieve similar ongoing savings. So we'll go to slide 35, where we showed some economic results for a few of the installations. This slide illustrates results from 3 investigators whose work is near final on the key economic metric. Results for 3 of the 7 installations, 1 from each of the services, are displayed on this slide. The percentage improvement or deterioration results compared to the baseline microgrid is what's shown on the bars. The negative results for Patuxent River and Fort Bliss were from a vendor modeling an emerging technology. That's a non-lithium ion technology that, while it has certain interesting performance aspects, has some cost deficits versus other battery systems. That contractor did not review Holloman, which is why there's no green bar on Holloman. Each of the investigators was asked to model 5 of the 7 installations, the 5 that best suited their solution. So going back to the results for the investigators whose results are represented by the blue and the red bars, for Patuxent River, which is in Maryland and Delaware and then PJM electric market, you can see that inclusion of the battery in the microgrid improved economics by 66 and 35% for the 2 contractors and reduced it by 31% for the third one. On the plus side, those percentage savings translate into about $500,000 of savings per year at the 66% level, and about $275,000 of savings annually at the 35% level. And that's after including all the costs of buying, integrating, and operating the microgrid, the battery and the microgrid. So you get all the reliability benefits while creating savings. You can see that the same two contractors had similar results at Holloman, where there were 44% and 40% savings achieved, which were material there. At both Patuxent River and Holloman, the savings originate from multiple sources, and this is important to understand. This is not a case where a battery is installed, it does one thing well, and that drives the economic case. There's a number of different areas where the addition of that to the microgrid can drive value. Retail bill savings, reduction in the number of diesel generators, in some cases reduction in the number of UPS, in addition to potentially extra revenues from PJM wholesale market participation for the Patuxent River base. A comparison set of results from NREL is on the next slide, 36. At the request of ESTCP, Dan Olis and Bill Becker at NREL conducted modeling of how much adding battery storage to the baseline microgrid affected economic results at all 7 of the installations. They used the REOPT tool, REOPT, which is a techno-economic decision support platform of NREL that optimizes microgrids and other energy configurations. REOPT recommends the optimal mix of renewable energy, conventional fossil fuel generation, and energy storage technologies to meet cost savings, resilience, and energy performance goals. So it was a tool well suited to this particular task. The NREL results displaying the percentage saving on the key economic metric, what does it cost to protect a kilowatt of critical load per year? They did so by adding a standard lithium-ion battery system to the microgrid. You can see that there are savings at all installations, which is an important observation in itself. Savings range from 5% at Fort Bliss on the low end to 36% at Westover Air Reserve Base. Higher savings were generally obtained for installations in structured wholesale markets because there's an extra revenue source there. And we'll talk about those markets in a moment. Savings are also higher where retail electric prices are higher. For a bit more detail on the sources of the savings, please go to slide 37. Here, NREL breaks out the incremental costs and savings from adding battery systems to 2 of the installations. March with a small critical load and Patuxent River with a large critical load. Now I should mention, like the investigator results, these are, consider these preliminary results, but well situated to review. First, you see the battery size at NREL's REOPT model selected. 0.6 megawatts of power and 1.7 megawatt hours for March, and 2.4 megawatts of power and 3 megawatt hours of energy at Patuxent River. You can see that in italics in the second row down. That is the optimal battery size row. So these are mid-sized to somewhat large batteries for commercial industrial customers. The cost of adding the batteries is $96 per kilowatt of peak critical load per year at March, and $19 at Patuxent River, where the battery cost gets spread over a much, much larger critical load. Then you can see the savings farther below in the chart. Demand response and wholesale revenue at Patuxent River almost pays entirely for the battery. $15 per kilowatt per year on new revenues versus a $19 cost for the battery system. In real dollars, this battery system costs about $150,000 per year, that's just $19 times the peak critical load of 8,014 kilowatts. Retail bill savings at that base are even higher at $26 per kilowatt and more than $200,000 annually. So more than the cost of the incremental cost of the battery system are the retail bill savings. At March, the retail bill savings are the biggest economic advantage, more than paying for the $58,000 annualized cost of adding the battery system. That $58,000 is just $96 times the peak critical load of 600. That said, adding a storage-enabled microgrid at March is still a very expensive endeavor on a relative basis, 5 times higher versus the much larger Patuxent River, $361 per kilowatt versus $68. That points to the need to find more standardized, low-cost microgrid solutions for reserve bases and other smaller installations. They have the same, mission-critical needs, just in terms of scale. Some, certain microgrid solutions are not going to be as appropriate there because they're not going to be as cost-effective. While size matters in terms of economics, so does geography, and we'll touch on that very briefly next on slide 38. This slide shows a map of the 7 installations that were modeled for this program. They represent a broad cross-section with installations in structured markets, looking from east to west of ISO New England, PJM in the Mid-Atlantic, ERCOT in Texas, and California ISO, where there are ample and growing opportunities for storage participation in these markets. There are also a couple installations, Fort Bliss and Holloman, that are in vertically integrated markets without as many participation options. To me, the most important takeaways from stage 1, the techno-economic modeling that was concluded largely in 2019 of this R&D program, are that you should measure energy security investments with clear reliability and economic performance metrics, and that adding batteries can improve outcomes, though you need to be very, very selective about where and how you add batteries to get exceptional results. This is anything but a one-size-fits-all solution. Please go to slide 39, where Jeff Marquesi will take back over to discuss how this R&D effort will unfold over the next few years and how individual installations can participate in and benefit from it. Thank you.
Thanks, Craig. So I'd like to just wrap up this webinar by describing our future plans, as Craig said. We go to chart 40. As mentioned earlier, ESTCP is initiating a phase 2 this fiscal year involving hardware-in-the-loop testing. We have learned from phase 1 that there is a significant value to DoD's mission needs in terms of improved reliability and cost effectiveness for certain storage-enabled microgrids. The fundamental question we want to answer in our hardware-in-the-loop is it feasible to actually engineer such a system to be stable and to conduct the functions that were assumed in the techno-economic analysis? So for those of you who aren't familiar with hardware-in-the-loop testing, on this diagram is a one-line diagram of a previous hardware-in-the-loop microgrid test done up at the National Renewable Energy Lab Energy System Integration Facility of the Borrego Springs microgrid. This was a microgrid done by the utility, supported by the California Energy Commission. And the design for the ESTCP hardware look will look different, but this illustrates the type of questions and the type of setup you can do in a hardware-in-the-loop, where you can put actual hardware, inverters for the PV, inverters for the battery itself, the microgrid controller. We will actually include a diesel generator and its controller as actual hardware with power flows and comm links between them. And then you can emulate those elements which you can't have in a laboratory building setting, the full grid effect, the feeder design and its response, as well as the loads and the actual power coming from the full-scale PV. And these can be established in a hardware-in-the-loop facility, which allows you to run in real time the performance of your controller and your inverter and battery hardware. This phase 2 of the project is starting this year. 3 of the teams that did phase 1 work have been selected to go forward in this, and it'll allow examination of solutions which looking at 2 different lithium-ion commercial batteries, systems with ultra caps and fast switching technology, as well as one of the emerging technologies of vanadium flow battery. The tests, the lead companies are listed there on the chart: Ameresco, Arizona State, and SRI, which was the team, and Raytheon. They will be run through a set of scenarios to prove that the assumed functionality in the techno-economic modeling can actually be performed. That is, operating while grid-tied, receiving appropriate signals, and doing the functions they claim to do to achieve the revenue or cost savings, be able to disconnect into an island mode, operating while islanding, where you're rarely dependent on the battery to manage the intermittent photovoltaic. We'll be looking at 2 type of feeder situations. One that sort of represents the Pax River case, where you have a modest level of PV relative to your peak critical load, and one similar to Westover, where the PV capacity is over 100% of what your critical load. This will allow us to understand the functional performance of these systems under real conditions in a very quick time frame at a relatively reasonable cost. As I said, this work is starting this fiscal year and should be completed during the calendar year. Now, slide 41. The phase 3 demos, which are scheduled for FY21, anticipate taking, some of these technologies, if successful, forward into an actual field demonstration on a military installation. We are very interested in identifying potential sites now. The attributes that are most critical to participate in this is obviously the first, an interest and a willingness to work with ESTCP to serve as the host for these demonstrations. And then either the existence or soon to be existing PV system, which could then drive the storage systems and the microgrid, which ESTCP would fund to do these demonstrations. If there are representatives from DoD installations and the services who are interested in serving in this, please feel free to contact me. The contact information is on the end slide, and we can have a discussion as we begin to explore what's possible out in the FY21. I think this will give the installations that serve as demonstration sites an experience to understand for their specific location the value of integrating storage with a PV system, which now provides economic value, but no military mission value in terms of energy resiliency, as well as, if they so desire, to maintain ownership of any equipment brought during the demonstration. Now, slide 42. Let me just quickly conclude to say and to repeat what Craig and I have said in earlier slides that we've learned in this ESTCP initiative. First is that storage-enabled microgrids can provide enhanced resiliency. And they could do this at a lower life cycle cost with equal or higher reliability than the requirements often set for a microgrid diesel generator only. I will repeat what is self-evident. All these reliability performances are much higher than given by current standalone generators. The FAIN run results will be released soon. Each project will have a standalone Petro report, which will be available on the web, and there'll be a synthesis report that is out by late spring, early summer, which will summarize and analyze the results of the 6 teams. The hardware and the loop tests are under contract shortly, and planning is underway, and those will de-risk and allow decisions made for the FY21 full-scale things. And as we look forward, as I said before, and if you know of installations that may be willing to host them, please have them contact myself or the ESTCP office directly. Slide 43. Both Craig and my email are shown on this chart. There's additional information on the CERTIP and ESTCP website. Please feel free to reach out to us directly if you have questions about that. But slide 46, Rula, I'll turn it over to you as we're happy to answer any questions now.
Great. Thank you so much, Jeff and Greg, for a very engaging presentation. So engaging that we got 23 questions. So we're going to get started here. The first one is from the Alaska Center for Energy and Power. And the question is, did the reliability studies you described include vulnerability and failure of the distribution system?
That's an excellent question. And the short answer is no, it didn't. One of the things is vulnerability of the distribution system is a key consideration. It will equally degrade the reliability of any microgrid system, whether it uses storage or not. I will say, though standalone generators are not directly impacted by failures in the distribution system, the overall energy resilience, even with standalone systems, is heavily impacted. So I think the bottom line for people with installations or even any community is a robust and reliable distribution system is a first requirement if you're interested in energy resiliency. That can be easily achieved some places and more difficult in some other locations, mostly driven by weather conditions and the state of past maintenance. But coming back to your question, that issue was not considered, and it was assumed the distribution system itself was up and operable.
And Jeff, and this is Craig, I'll add to that. It is an excellent question. And in the hardware in the loop phase, which is being conducted this year, that issue will be confronted head on, because as part of that, there's what's called a feeder model. So there'll be actually a circuit model that'll be reviewed, and the result, the same configuration that was done in the economic phase will be modeled in a much more rigorous way with actual hardware in the loop and the controller operating with all the vulnerabilities of the feeder model, which would parallel, you know, inside the fence distribution conditions at the installation. Jeff, I don't know if you want to add.
No, that's great.
Great, thank you both. This second question relates to your phase 1 installation baseline economic analysis portion of the presentation. It's from NAPAC Southeast from PWD Guantanamo Bay, and it relates to the Fort Bliss discussion. Can't Fort Bliss get any savings as such a large consumer?
Craig, why don't you respond to that?
Yeah, that's a great question. So the short answer is Fort Bliss has already achieved those savings. So what we did as part of this program, because we wanted to have realistic conditions, Fort Bliss shared with us the tariff that they're on, and what they've already, with their utility, El Paso Electric, taken advantage of that they have backup some large-scale fossil fuel generation there, and the way they've structured their supply and tariff arrangement with utility means that they've already captured most of that value. Therefore, they've limited additional opportunities for savings. So they have a very large base, they have very high peak demand charges, but they've already managed those down through their actions with their utility. And that was an important part of this analysis. Was, you know, some installations have already done that, so there's less opportunity for savings, and that's what happens in the real world as well. Others really haven't been able to penetrate those savings yet.
Great, thank you. The next question is from 128 Air Refueling Wing. Can you please comment on how battery system inverter sizing can impact the performance? For example, did you consider smaller battery capacity with a larger inverter capacity to meet short duration demand?
So the size of the inverter was a variable that the individual research teams optimized on. And when the reports come out, you'll see that they vary considerably between the systems, and it is an important variable. This was not something the program office set, and it's not a standard across the modeling. They were optimized along with the battery energy and power size to ensure what they thought was the most cost-effective solution. So it's hard to give you any general answer to your questions. The details depend on each specific modeling example.
Great, thank you. This is a question from an anonymous attendee, and it relates to the reliability baseline analysis. And for this analysis, the question is whether it's appropriate to assume maintain generators on military installations, and if so, if yes, why?
So, if I understand the question, so the reliability of the individual diesel generators on military installations is very sensitive to maintenance procedures. There is guidance out there in UFC, which is very similar to industrial guidance, which produces well-maintained generators. Unfortunately, it doesn't happen. The generators that are on military installations are very similar to those in the commercial space, and they're all the standard US manufacturers, and those were what were modeled. Now, one thing I didn't say earlier, and I'm happy if someone sends me an email, we have written a detailed paper on analysis of generator data for military installations. and explained the expected reliability of those and where the numbers come from. It has been submitted to a journal, and it'll be in a government report this spring, but I'm happy to send people a preprint of that if they're interested in seeing the underlying data.
Great, thank you. Did you consider the cost of disposing of batteries once they have exceeded their usable life, specifically lithium-ion batteries?
Craig, do you want to comment on that?
Yeah, I don't believe that again was also left to the discretion of the investigators how they characterize the life cycle cost of the battery. I don't believe that they created any, either. I think they typically had a zero net cost at replacement. So the battery component of the battery energy storage system typically needs to be replaced depending on use cycles and age at some point during the 20-year investment cycle. And I believe the assumptions of most of the investigators were that the net cost would be zero. So just any disposal costs would be offset by any end of life value they might obtain for it. But that is something that would be detailed in the individual investigator reports.
Thank you, Craig. Another question from the Alaska Center for Energy and Power. What were the battery energy storage system reliability parameters, and how were they determined?
Yes, Jeff, that's an excellent question. It's actually probably the most uncertain parameter in all the modeling. Each investigator working with their suppliers provided an estimate with a justification on what they believe the reliability of the storage system is. It is assumed to have driven mostly by availability issues, but reasonably high. The literature on this is sparse, and the data is mostly proprietary and not shared. So the assumptions made were reasonable, sort of 90+% availability and things like that, and they vary by their specific technology. But it is an assumption, and the results are dependent on it. You can see we will be doing some analysis in this synthesis report, which uses that as a parameter to show the impact of that assumption. But to be honest, given the relatively young nature of the large-scale stationary storage industry, reliability numbers are hard to trust fully. And so that is an ongoing area of concern.
Yeah, and this is Craig, and I'll add that as Jeff pointed out, it's a key question. ESTCP in working with the investigators really focus on that in it. So you'll see in their reports that they detail a number of metrics. As Jeff points out, it's not like PV reliability or diesel generator reliability, which is not well understood, but it's a mature technology. But they worked hard at trying to represent that fairly. And I believe every investigator team had a partnership or a good relationship with storage providers and was able to conduct, it was important to the validity of this effort that they conduct research and outreach on actual parameters of operating systems. So you'll see a lot of that detail in their reports.
Thank you both. How are the assessments and analyses you described different than the Office of the Secretary of Defense analysis tool that looks at performance and life cycle costs?
So I assume the question is asking about the MIT Lincoln Lab tool that was sponsored by OSD. That's very much a screening level tool, and it does not conduct the level of economics which is realistic for an individual installation. So, we think about modeling and assessments. There are very high level tools, which I think the MIT or the OSD tool is, which can give you some broad view of what's happening, but it doesn't factor in, for example, all the issues which drive a site-specific revenue saving estimate, the structure of the individual tariff, the market conditions, whether it's been an open market or whether it's still vertically controlled. In addition, there is not a lot of assessments of how you would combine PV and batteries in that tool in a way which allows you to reduce the number of diesel generators. So I would say this analysis done here is at a much higher fidelity. It is still a modeling result, and we require some hardware in the loop testing to validate the claim performances. But these are much more realistic in terms of what to be expecting from both performance as well as cost and an installation. I'll also add that, because I've worked with the people who developed that tool, and they were under the constraint that there was, until our recent work sponsored by ESTCP, no published data available on expected reliability of emergency diesel generators that could be used to do modeling for islanded conditions. So their assumptions for the generators, which were not unreasonable given the lack of data, turn out not to be quantitatively correct. And reliability, even when well maintained for diesel generators, is much worse than is in that tool. And obviously, poorly maintained generators are even much worse. So even the reliability estimates for just purely diesel systems will differ considerably between the ERA tool, which is the OSD tool, and these analysis, which are being published shortly and can be recreated for any given institution.
Thank you, Jeff. Have you considered the additional reliability if the net PV generation and storage is sufficient to become a net exporter of energy?
So let me tackle that first, and I'll ask Craig to contribute. So one of the constraints in this study, which may not be true at all installations, but it was part of the experimental design, was we preset the power level or capacity of the PV system and did not let that be optimized. And I think to do what you're talking about, one would want to make decisions in combination of storage and PV together. So in other words, the PV capacity wasn't allowed to be changed for the given system. And some of the investigators explored that on their own, and that can have a significant effect. The reason we structured the experiment this way is many of the decisions for building, either through power purchase agreements or enhanced use lease or through MILCON funding at military installations, on-site PV, have already taken place. And so you're not having the luxury of doing a full optimization design, but not always. And I think the question you're raising would have a big impact if you have flexibility on the size of the PV. Craig, did you want to add to that?
No, that's exactly right. So, the focus of this effort was really to isolate the value of storage. And you can, because PV is so cost effective in many installations and lower than conventional utility prices, if you just add a lot of PV, it would make the economics look great, but it's not because of the battery, it's because of adding PV. And and as Jeff pointed out, some of the investigators sort of did side cases to describe that. The other aspect of this that some of the investigators highlight in the reports is if you pair PV with battery, you can claim the investment tax credit. If you pair it sufficiently and it's charged from the PV, you can get investment tax credit on the storage, which reduces its effective capital costs. And that was also shown in some of the reports, and you'll see the results of that.
Great, thank you both. This next question is from MIT Lincoln Lab. One of the challenges faced by simulations is providing results that align with those actually experienced by the installation. As you progress in each phase of your program, can you explain how you will adjust the model to better reflect reality, both in terms of cost and performance?
Yeah, that's definitely a true statement. And so the phase one, as we talked about originally, was designed to answer a question, is there value here that's worth further investment, and at what magnitude? and what are the potential solutions. And so it allowed us to look quite expansively in terms of different market conditions, different sizes, but simulation allows you to do that. But as the folks at MIT, because they've been very involved in some of these work, as you go to, it doesn't allow you to have full realism on a lot of issues. And so our hope is that we've been able to explore broadly the economic issues through this, but stability issues and control issues really are a bit of a leap of faith based on techno-economic analysis. And that realism we hope to incorporate in the testing and the hardware in the loop to look at much more variable PV and high frequency changes, as well as load profiles, which are not simply smoothed as an hourly load profile as well, and to allow different issues of a specific feeder system. That allows you to explore some things, but now you can't be doing it for dozens of different feeder configurations, but it allows you to still explore a lot of issues. The truth in the end gets proven by doing something in the real world, and here you have the most realism because you're actually testing it under real conditions, but it's a, one might say, an N of 1 experiment, or maybe an N of 2, if depending on resources, where you can only do the demonstration at 1 or 2 facilities because of the cost and such. And so it's a trade-off between breadth of variables and realism of them. And one of the reasons to structure the program in this 3 phases is to try to solve that trade-off by doing it in steps. And I think we'll end up with robust answers at the end, but there are certain issues that you'll never fully understand until you actually go to a demonstration. And the long-term economics, you know, we've modeled by looking at different variability in market conditions, but in the end, none of us have a perfect vision of the future market conditions in the energy market. So a 20-year life cycle cost estimate could be changed if the market significantly changed 8 years into the life of a project. And so there are some uncertainties. Craig, is there anything you'd like to add to that?
Yeah, it's an excellent point. And the only thing I would add is that one of the things we're asking the 3 investigators doing the hardware and the loop testing to do is to compare the results they get on the performance and the economic side. You know, the most important thing is what are those results, what do they mean for DoD, and what do they imply for field demonstrations. But as a secondary objective, we are asking them to compare the results they get from hardware and loop testing to the earlier modeling to identify if there's any major differences. We want to identify, well, why did those occur? Were there biases? Were there flaws in the modeling approach that weren't as realistic? And you know, I think that's important to surface as well.
Wonderful, thank you both. Maybe we'll do one more question before we wrap up. This is a question from the Arizona State University. Can you please speak to how solar PV capacity can affect optimal sizing of storage and results? Specifically, if more solar PV capacity can be added, how might that adjust optimal battery sizing, reliability results, and financial results?
Yeah, no, it's a good question. It's sort of related to one of the earlier questions. Look, PV is highly reliable, but very intermittent. So the current modernly deployed PV in this country has extremely reliable inverters, and the modules themselves are very reliable. And most, for large PV, you know, multi-megawatt PV, you know, it's rare that a failure can lead to anything but a modest degradation of the output. But PV doesn't produce steady power. It's very obviously dependent on solar conditions, which are dependent on weather. So having said that, increasing PV, you know, where it's economically advantageous, you know, improves the energy life cycle costs at large for an installation greatly. How that plays into the size of the storage is a very site-specific modeling question. And it also will depend. We've set this experiment up to ask the question, let's say your primary goal is to meet the reliability criteria for what potentially outage as long as 1 week. But if you have certain loads at an installation which are non-transferable, can't be moved in case of a long-term disaster, you might very much have interest in a sub-portion of your critical load to be able to support for months, right? And there, depending on the size of that load and your battery, you might change or increase your PV. It's hard to give a single simple answer, but if you have that option to play with that variable, it can also provide, as I'm sure Craig will comment on, a lot of other economic advantages depending on the market you're in terms of self-consumption increases and things like that. Craig, do you want to add to that?
Yeah, the only thing is I would add are, obviously the duration of the batteries can be very important. The question is sort of, as Jeff pointed out, what's the configuration of your other assets? What does your load shape look like? How much is PV going to be? How long, what sort of reliability function is it providing? Longer duration, shorter power transitions, things like that. The only thing I would add to it is that it's critical that the PV be configured properly to be utilized with microgrid. So, I know ESTCP has additional topics for investment that went out this year that look at that issue of resiliency, which is, within this R&D program, you'll see sort of the relationships between all the variables that play out on a sort of installation-specific basis. But more broadly, there's a number of PV assets and military installations that have potential energy security benefits, but those cannot be practically obtained today because of the way the PV is, in essence, configured. And how to integrate that into resiliency in the future is, I think, is a really important topic beyond, the relative scale is very important, but there's sort of a threshold issue of, is it configured for security or is it configured entirely for economics? Not that configuring for economics is entirely, there's anything wrong with that, but I think, there's some assets that are configured for limited resiliency purposes. So it's really important to sort of distinguish what's the use case of the PV at each installation for when you're looking at the resiliency.
Let me just add one thing to sort of a closing comment on all this work on storage. So keep in mind that this was an ESTCP set of analysis with follow-on demonstrations. So we were constrained to storage technologies which are either commercially available now or are emerging commercially. They may be, version 1, but, and that really constrains you to storage durations of handfuls of hours at most. There is a lot of research going on, particularly in RPE. They have their DAYS program, if you're not familiar with it. And there's other work going on in the country, which is looking at, can we develop affordable, not, tens of hours, but hundreds of hours of storage that would allow us to do different things with storage. I keep in mind that I think of this as iteration 1 in an evolving world of storage. This is giving us insight of what we can do with today's technology. We see significant value and benefits and need to further examine and improve that. But I think within the next decade, we may have a second revolution, which might not be lithium-ion batteries, which for stationary storage could add a totally qualitatively different optimization problem where the storage capacity is an order of magnitude larger than commercial things allow us today. So keep that in mind. This is not a technology which is at the end of its life. We're in the early stages of advanced stationary storage.
Great. Thank you so much, Jeff. And thank you also, Craig. This has been a wonderful and engaging webinar. At this point, we're going to wrap up, but remind you all that our next webinar in the Startup and ESDCP webinar series is on Thursday, February 27th. It will be in the Weapons Systems and Platforms program area, and it will detail results from DoD research efforts on the development of environmentally friendly pyrotechnic and propellant formulations. This webinar will feature two speakers, Mr. Matthew Puzienski from Innovative Materials and Processes and Mr. Mike Miller from Resiliency Corporation. Registration is open, so please visit the Startup and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it, as Tim mentioned, if you could please take a moment at this time to complete a very brief survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.